Hello APC Mechanics students in Unit 6 Oscillations, Class 7, 6.1 Pendulum Motion, Part 1. Then let's start with Section 1 Pendulums. Simple harmonic motion can be demonstrated at the level of the pendulums. In this course, we'll go over three types of pendulums. The simple pendulum. What is a simple pendulum? In which a mass, a point-like object, called the bob, is connected to a light string that makes an angle theta with the vertical, so a point particle connected to a string of negligible mass. The physical pendulum, a rigid body that can rotate about an axis shifted from its center of mass. Now this is the axis of rotation which is shifted from the center of mass, then this rigid body can oscillate around this point. And a torsion pendulum, where a rigid body that can rotate around a torsional wire. This is the torsional wire that have some elasticity and can drive the rigid body into oscillations. Then we'll initiate with the simple pendulum. Now Section 2, differential equation of a simple pendulum, the simple harmonic motion. We have visited the simple pendulum throughout the course in several places. The simple pendulum consists of a mass string of length L and a point particle of mass m that can oscillate with an angle theta around the vertical. Before we derive the differential equation that governs its motion, let's review things that we have dealt related to the simple pendulum. Now recall, the equilibrium position is when the string is along the vertical line, so that's the equilibrium position. Okay. Now during the downward motion, the object is speeding up and has both acceleration, centripetal and tangential. The tangential acceleration has the same direction of the velocity because we're speeding up. Now because the bob of the pendulum occupies a circular motion, then we expect that at most times we would have centripetal acceleration and tangential acceleration whether we're speeding up or slowing down. So let me repeat again and say, during the downward motion, the object is speeding up and that would produce tangential acceleration. First of all, let me say that we have, so if this is the amplitude that we'll discuss and that's the equilibrium position, at a point between the amplitude and the equilibrium position, the bob is speeding up, we're going down. So first of all, we have centripetal acceleration and we have tangential acceleration because we're speeding up, and that would be the total acceleration. During the upward motion, the object is slowing down and has both acceleration, centripetal and tangential. The tangential acceleration has an opposite direction to the velocity. Now this is the centripetal and that's the tangential. Notice that here the pendulum is moving in this direction, however here the pendulum or the object is moving in this direction, and the total acceleration would be given like that. At the equilibrium position, the object is not gaining speed anymore, then the object has only centripetal acceleration. Now remember that for the harmonic oscillator, we said that because the acceleration is proportional to the displacement, at the equilibrium position, the displacement is 0, so basically the acceleration is 0 and we have maximum speed. So here it's exactly the same. At the equilibrium position, the position, which is basically theta, the angle with the vertical, would be 0 and that would be proportional to the acceleration, but which acceleration? That would be the tangential. For this reason, we don't have any speeding up or slowing down at the equilibrium position, we only have centripetal acceleration. And at extreme positions, the object has only tangential acceleration and the centripetal acceleration is 0 since the speed of the object momentarily becomes 0. So at the extreme position, suppose that the object is going up and reaches this position, so it's gonna change direction, and this happens only if momentarily the speed vanishes. If the speed vanishes, we know that the centripetal acceleration is given by v squared divided by r, so that would be 0. So we're gonna have 0 centripetal acceleration at extreme positions. However, we would have tangential acceleration which is maximum at the extreme position, like that. And that would be again the total acceleration, and this is also the total acceleration in this case. Now remark, the dynamics of a simple pendulum is not straightforward, as we have seen. And for a very simple reason, the acceleration is not constant, which means cannot be handled easily using Newton's second law. Recall that for problems related to the motion of the pendulum like the one below, which has to deal with the motion of a free rotating rod, it has been treated with the conservation of energy and not Newton's second law, because for the reasons that we have specified. However, in today's class we will dictate the evolution of the system using Newton's second law, which requires the promotion of a differential equation. Now, section 2, differential equation of a simple pendulum, simple harmonic motion. For that, consider a simple pendulum made up of a massless string of length L and a point particle of mass m known as the bob. As the bob swings, the string makes an angle theta with the vertical. Theta represents our variable of motion. Then we're interested in determining differential equation that governs the evolution of the system for theta. We will put forward few assumptions. Then let me start. Assumption 1, the string is massless, so there is no mass for this string. Assumption 2, the bob is a point-like particle, so there are no dimensions for this bob. Assumption 3, the angles of oscillations are very small, theta is less than 15 degrees, and I will state how much important is assumption 3. If we ignore assumptions 1 and 2, the simple pendulum would be treated as a physical pendulum, also that we will visit in class 8. Assumption 3 is important. Why? It allows us mathematically to use the following approximations. Cosine theta would be approximated as 1 minus theta square over 2, and sine theta would be approximated as theta. Why these are important? Because now we're gonna apply Newton's second law and we need to project forces. And whenever we're projecting forces, we might expect either cosine theta and sine theta. In the differential equation itself, if we have cosine and we have double derivative or double derivative with sine, that it's so difficult to solve analytically. For this reason, we'll assume small oscillations in order to apply these approximations. These relations hold true if the angle of oscillations is very small. They are very helpful in solving differential equations analytically. The forces that are acting on the bob, now we have the pull of gravity, so that's the bob, that's the string, that's the angle theta with the vertical. We have the pull of gravity down, we have the tension in the string, and now we're gonna apply Newton's second law for translation. Even though the pendulum performs as a circular motion, we're gonna apply Newton's second law for translation. However, you can also apply Newton's second law for rotation, and you can check by yourself that it works. Now, F naught is ma, we have the pull of gravity plus the tension is equal to ma. This is a vector equation which gives the birth of two linear equations depending on which direction we're gonna project. Now, we're gonna project along the tangential direction. This is the tangential direction, so let me specify the angles. Now here, this is the string that makes an angle theta with the vertical. All of this is the direction of the string. This is another vertical because the pull of gravity acts vertically downward, and this is again the angle theta. And now we need to project the equation. Remember that in the simple harmonic motion, we said that the restoring force should be preceded with a minus sign. Now here, what is the force that is playing the role of the restoring force? And actually it's the pull of gravity, because if you think about it, the pull of gravity has two projections. Projection like that, given by mg sine theta, and another projection is given like that, which is mg cosine theta. Now this component will cancel with the tension. For this reason, there is no motion along the string, and the mg sine theta would be the component of the pull of gravity that is responsible to pull back the bob into its equilibrium position. For this reason, because the pull of gravity is playing the role of the restoring force, here we have added a minus sign, and this is very important. And it's not about the positivity or the negativity of the direction. It's just because we understand that the pull of gravity, it tries to pull the bob into its equilibrium position along the equilibrium line. So this is a restoring force. And that would be minus mg sine theta is equal to ma. Now let's unify the variables at least. Or let me say that theta and a are two variables. A is a variable as we have discussed. Now they can be unified using some relations and calculus. We know that this is linear or tangential acceleration. It's related to the angular by given r multiplied by alpha. Here the radius is given by the length of the pendulum itself, and we know that alpha again can be related to theta using a double derivative, and we would end up having the following equations. Equation mld square theta by dt square. Now m with m cancel, and we're left with minus g sine theta is equal to ld square theta by dt square. Assuming that the bob is performing small oscillations, and using the approximation that sine theta is equal to theta, and replacing this in the differential equation, we would end up having the following. And here let me state something very important. Remember that assumption 3 states that these relations hold true if the angle of oscillations are very small. Now if you take a look at this differential equation, and if you move this to the other side, we would end up normalizing the second order derivative. We would end up having d square theta by dt square plus g over L sine theta is equal to 0. And if you compare this with the following equation, which is x double dot plus omega square x is equal to 0. Now here we have x or theta, so let me say that this is theta double dot plus omega square theta is equal to 0. If you look carefully, here we have the sine function and here we have theta. So this equation doesn't agree with the form of the simple harmonic motion, so we cannot say that this is performing simple harmonic motion. The presence of these trigonometric functions destroy the symmetry of the simple harmonic motion. However, if you consider that the oscillations are very small, then we can use that sine theta is equal to theta, and replacing it here and dragging it to the other side and reading the equation from right to left and normalizing the coefficient, that would be d square theta by dt square plus g over L theta equals to 0. Then for very small angles, a simple pendulum performs small oscillations, and the differential equation that governs the motion is given by the following, which satisfy the following form, which is theta double dot plus omega square theta is equal to 0. And here we can notice or feel the importance of assumption 3. What is the interpretation? Since the obtained differential equation satisfying the form theta double dot plus omega square theta is equal to 0, then the type of motion is simple harmonic motion. The angular acceleration is proportional to the angular position. Alpha is minus g over L theta, and the restoring force here would be the pull of gravity. So remember that we started by defining the simple harmonic motion in class 1 to be a motion in which the acceleration is proportional to the displacement, and there must be a restoring force which drives the object into oscillations. And it's exactly the case here. How come the acceleration is proportional to the displacement or to the position, as we have seen from this equation? Alpha is the acceleration, theta is the position. And what is the force that's playing the role of the restoring force is basically the component mg sine theta of the pull of gravity, and that would be preceded by minus sign. The angular frequency and the period of oscillations of the pendulum are given by. So if you compare this form with this form, you will notice that omega square is given by g over L, which means that omega is given by square root g over L, and the period would be given by 2 pi square root L over g. And then omega is given by that, and the period is given by that. And here, something important that we should mention, if you remember in the previous class, we have solved several exercises, and we tried to play with the value of g for horizontal, inclined, and vertical oscillator, and we've noticed that doesn't affect omega and the period. However, for a simple pendulum, g will affect omega and the period. However, the mass is not important. The length of the pendulum is important. An important result to point out is that the angular frequency and the period are mass independent. They don't depend on the mass, they only depend on the length of the string and the value of g as well. The solution of the differential equation is given by theta, which is theta m sine omega t plus phi, or a cosine function, where theta is the angular position of the bob, and the solution of the differential equation, the SI unit is not degrees but radians. Theta m is the amplitude of oscillations known by A, also radians. Now cosine and sine are modeling functions, they are dimensionless quantities. Omega is the angular frequency and phi is the initial phase difference and can be determined based on initial conditions, and its unit is given by rad, which is radians. And now for the rest of the video, we're gonna solve some exercises. Exercise 1, a pendulum with a period of 1 second on Earth where the acceleration due to gravity is g is taken to another planet where the period is 2 seconds. The acceleration due to gravity on the other planet is most nearly. Now, because we didn't discuss or they didn't mention much about what is the nature of this pendulum, we're gonna assume a simple pendulum in which the period is given by 2 pi square root L over g. And we're interested in determining the value of g on the new planet. So what would happen here is the following. So we would say that t square is equal to 4 pi square L over g, and we're interested in the value of g, so g is given by 4 pi square L over the period square. And if you notice that from the choices, it seems that we're gonna apply the factor of change, and we will simply double the period. Now this is invariant, so that would be 1 divided by 2 to the power of 2, so that would be 1 over 4, and the correct answer would be A. And here, as you can notice, that the pendulum, although it's very simple, but it can be used to measure the value of a g on a planet by simply measuring the period using a stopwatch. So this is super important, and we know that the value of g of a planet is very important for us. A simple pendulum consists of a 1 kg, the mass is not important, on a string of about 1 meter long. It has a period of 2 seconds. The pendulum would have a period of 1 second if you notice the choices, the mass is not important for us, neither the amplitude, so it's gonna be either A or B. Now we know that the factor that affects the period is basically the length, so let's calculate the new length in order to determine whether it's 0.25 or 2. Also, if you think about it, the period is given by 2 pi square root L over g. Now the period decreases. The only way that the period decreases if L decreases, so the correct answer going from 1 meter long to decreases, it would be A, and we can check that by calculation. Pi square, a t square would be 4 pi square L over g, and L would be given by gt square divided by 4 pi square. Always remember, a good approximation is to use pi square is equal to 10 whenever the numbers seem to be perfect. Then that would be 10. The new period is 1 to the power of 2, 4 multiplied by 10, 10 with 10 cancel, that would be 1 over 4, which is basically 0.25 meters, making A to be the correct answer. A simple pendulum is constructed by hanging a ball at the end of a string. The pendulum has a period of 1 second on Earth. Which of the following could allow the pendulum to have a period of 1 second on the Moon? We know that the period is given by 2 pi square root L over g. Going from Earth to Moon, which means that g decreases, we need the period to remain the same. If the period is set to remain the same, we need to decrease the value of L, which means D would be the correct answer. In an experiment with a simple pendulum, measurements of the period of the pendulum are made for different values of its length, L. When plotted on a curve, which of the following should result in a straight line fit of the data? So we're trying to plot t versus L. We know that t is given by 2 pi square root L over g. So this should be linear. Let's square the period. Period square would be 4 pi square divided by g multiplied by L. So the only way to do it is to do or plot t square versus L, which is D. A simple pendulum has a period of 2 seconds for small amplitude oscillations. Why small amplitude oscillations? In order for the differential equation to be simple harmonic motion, in order to make use of these solutions. Which of the following equations could represent the angle theta that the pendulum makes with the vertical as a function of time t? Notice that all of them has an initial phase phi to be 0, and the function would be given by theta m sine omega t. Now omega is given by 2 pi over the period is given by 2, so 2 pi divided by 2, that would be pi radians per second, and the correct answer in this case would be B. And finally, this exercise as an exit ticket for today's video. A simple pendulum has a period of 2 seconds for small amplitude oscillations. The length of the pendulum is most nearly, so why small amplitude oscillations is important for us? In order to make use of the simple harmonic motion, which means that would be 2 pi radical L over g. we need to find the length. Then t square would be 4 pi square L over G. Then L in this case, if you isolate it, that would be t square G over 4 pi square. Number seems to be perfect, which means we can make use of the fact that pi square is equal to 10. Then t would be 2 to the power of 2 multiplied by 10 divided by 4 multiplied by 10, which means that L is 1 meter, making D to be the correct answer. Then that's it for me in this video, guys. See you soon in a new one.